Probability-based learning is a little different from the other machine learning uh, algorithms that we've went over, such as SVM or mm, or even deep learning, because this is more heavily involving statistics and probability. So basically, for this lecture, the probability, because in statistics there's two schools of a frequentist approach and a Bayesian approach. So the probability-based learning that we'll cover today is more towards the Bayesian approach. So it's basically making predictions by estimating and continuously updating the likelihood of different outcomes as the new information is collected. So for this slide, um, we can think about playing a game which is to find the queen from three shuffled cards, which are queen and the ace of clover and ace of spade. So you want to pick one of the um the cards that are upside down so that we can find the queen. So since this is a Bayesian approach, in the beginning, our initial belief for the likelihood of the cards being one of them, one more person has come, would naturally be 33% for each of the cards, which you can see in the right bar plot that the likelihoods are same for each. And one caveat here is that the likelihood term that's being used here is not the strict statistic likelihood, because you may have learned from a statistics course where there's a distinction between the likelihood and the probability, where the likelihood is trying to explain see how well a specific set of the model parameter explains the data, whereas the probability itself is trying to quantify the chance of observing a specific data given underlying model parameter. So in this case, this likelihood term is just being used as the empirical probability. So as we play multiple rounds of the game, such as the card revealed card correspond to, let's say, correspond to the current result of the game, where the queen is apparently in the center slot. So as we continue playing multiple rounds of the game, our estimate of the queen's position might be updated as we observe more and more information. So the right bar plot indicates that throughout multiple rounds of the game, we have seen the queen appearing in the center slot and sometimes in the left slot, but so far we have not seen it appearing in the right slot. So we are changing the estimation as we play the game. So what use would this bar plot be? What would be the utility of this bar plot? So that would be when we make predictions. So if you want to predict in the next round of the game where the queen appears, if our current estimation corresponds to the left bar plot, we would say that we would make our best guess would be that the queen would appear in the center, since that's what basically what we have seen so far throughout the game. Okay, so when we work with a probability-based learning, this is one example of a data set that we can work with. So as we can see, this is this is just a tabular data with 4 binary features, and 3 of them are the features that we use for prediction, such, in other words, descriptive features, and 1 is the target feature. So here, the meningitis is the target feature, which we want to. One more student has come. Make prediction, and the first 3 features, the headache, fever, vomiting, are basically the symptoms. So we're trying to see if each patient, so each row is whether each patient had a headache or fever or vomiting, and whether that patient was diagnosed as having meningitis or not, which is one form of disease. Okay. So directly from this categorical data set, we can derive the probabilities. So for the marginal probability of having fever or not could be obtained by just counting the number of the true values out of the total number of instances, which is 40%. And also we can directly derive the joint probability of having meningitis and headache by just looking to the occurrences of both being true. Yeah. Yes. So we can so the main point I'm trying to make is that we can just directly count each of these different types of probabilities as marginal probability, joint probability, and also conditional probability of the last bullet point, where it's the probability of having meningitis, given that the headache is true, would be to first narrow down to all the rows that are true with the headache, which is because we know that the conditional probability is by definition the joint probability divided the conditional. So from the headaches, we see the where both are true again, which is, I believe, 2 instances, which is 2 out of 7, which would correspond to 0.85. So the takeaway is that we can directly count all of these type of probabilities from the tabular data. Okay. So now, so when it comes to the joint probability distribution, so one joint probability itself that we saw was just the fourth bullet point correspond to one joint probability of seeing 2 events to get more than 1 events together. So these were 2-dimensional in terms of the number of features or the joint probability. But when you talk about the joint probability distribution, it's referring to all the features that we have, which are 4, all the 4 features, and all of the combinations of their unique feature assignments, such as since we have 4 binary features, the number of the unique assignments for those 4 features would be 2 to the power of 4, which here there are 16 unique features, where each of the cell, as this bullet point says, is a multi-dimensional, meaning it's 4-dimensional. So the reason for this joint distribution, full joint distribution table being important is because we can derive all kinds of probabilities by leveraging this joint probability distribution. So in other words, this joint probability distribution serves as a complete probabilistic model for all of the features that we can leverage to extract marginal features or marginal probability or conditional probability or other joint probabilities. If anything is unclear, please let me know. Okay, so the specific example of how we will try to derive each probability is many of you guys might be familiar with the concept of marginalization, which is in short, we are just summing over all the mutually exclusive possibilities for unwanted variables which we are not interested in. In other words, if we are just interested in deriving the marginal probability P of headache, this pH is equivalent to headache being true. Headache being false would correspond to the negation of H, just so you know. So if we are just interested in deriving this small probability for this 4-dimensional joint probability distribution, then we would want to marginalize across other features that we are not interested in, which are fever, you believe the V is vomit, and meningitis. So we just want to ignore but account for all possible different combinations, mutually exclusive possibilities for those 3 unneeded variables, so that we can just directly derive whether the probability of headache being true. So we are summing over all of the unneeded feature combinations where the headache is true. Is everything clear so far? Right. So by summing this first column, we will be able to directly derive the marginal probability of pH. So that's one example of deriving a probability from the table. And also, similarly, when we want to derive the joint probability of PHF, where probability of headache being true and fever being true occurring together, then now we are uninterested in variables of vomit and meningitis. So now we again marginalize those, which will correspond to adding all of the cells where you have H and F are true and account for all the possibilities for the unneeded variables, which will provide us with the joint probability. And if we can compute any marginal probability and joint probability, automatically we can compute any conditional probability using the definition of the conditional probability, the formula. Okay, so now since we know that so the reason for going over all of this deriving the probability out of the table is because later in the that light-based classifier, we're not exactly going to have a joint probability distribution table, but still we will have to um, count and count the occurrences from a table and then prepare pre-computed probabilities so that we can make predictions. So uh, okay. So I guess to put it more clearly, the reason for going over this slide of joint probability distribution is to show that it's a foundational source where we can derive likelihood or marginal probabilities, which will be used for the Bayesian inference. Yes, so this is the underlying probabilistic model for probability-based learning. Okay. Okay, so for this Bayes rule, many of you guys might have already went over this with Jacqueline, but we could go through it once more. So first of all, for the Bayes theorem, right? So for the Bayesian approach itself, unlike the frequentist approach, which the frequentist approach is just treats the probability as outcome from a many repeated experiment. So it doesn't really have any belief in the probability. It just treats it as a long run of frequency of events. But the Bayesian approach treats the probability as a measure of belief and then updates that belief when they get new data or new observation. So here we can understand the numerator of this formula as we start with some initial belief p of x, where first of all, x, we think of it as a hypothesis. And y is the observation. Or in more practical classification example, we can treat x as think of it as a class, where this data is, so then the y would be data. So the hypothesis here is that this data is this class, such as this patient should be diagnosed as having meningitis or not from the previous categorical data example. So we first have a prior belief on whether the probability of having meningitis. I'll just use the term disease instead of meningitis. So based on some previous study or some expert opinion, we might have some initial idea on the probability of having a disease. And then as we gain some new data, which this term is basically the likelihood. So it's the probability here of the data being aligning with our hypothesis. So in other words, how well does our hypothesis support or explain this given data? So for the meningitis example, this could be, let's say, the data of interest is this patient has headache, has fever, but does not vomit. Then how well does our hypothesis of having a disease explains it, which is the definition of the likelihood, which for some of you, right. So from the above two terms, this will serve as updating the initial belief based on the observation, the new data, which will provide the posterior, the updated belief based on the new data. So this is the high level idea. And the denominator, which we will go over, is just the overall probability of observing the data, regardless of the hypothesis, meaning that our current hypothesis is having, I think two more students have. So yes, the denominator we will go over in the next slide, but it's basically we're accounting for all of the other states for the target feature, such as accounting for not only having meningitis, but also not having meningitis, which we'll go over in the next slide. So formally, by the law of total probability, we can expand, this can be expanded, where y was the observational data, as has been marginalized or summed over all of the formerly hidden variables, but in this case, the target variable. So if the numerator of the Bayesian rule was accounting for one specific state of the target, which was having a meningitis, when we expand this observation through, which was marginalized, the I would correspond to x1 would correspond to having meningitis, and x2 would correspond to not having meningitis. So naturally, we can see that if we just think replace, just ignore eta, but replace the denominator and replace it here, we can see that this has a normalization effect because we are dividing a specific instance by all of the other possibilities. So in other words, in the previous, and if anything is unclear, please let me know through chat, or you could use the microphone. So to recap, when we try to update our belief of our hypothesis, which is the posterior probability, we start with some initial belief and likelihood, which explains the current observation or data, assuming that our hypothesis is true, the likelihood. Then we normalize it with the probability of observing the data itself. And that also aligns with the conceptually, because the left term is a posterior probability, where probability should be bound by 0 and 1. And for likelihood, for discrete variables, usually it can, since for the reason we want to normalize this, because the likelihood itself may not be always be summed to 1, meaning if, say, we compute across different hypotheses given one data, where this x1 would be having meningitis, x2 would be not having meningitis. And then sum them. This may not be equal to 1, but if we normalize each term by their sum, then their sum would become 1, which aligns with the definition of probability, which can be helpful, which is straightforward for interpretation and can be helpful for future application. So now when we now we would want to leverage the Bayesian rule in making predictions, the Bayesian prediction. So if we have a query instance, other words, I think one student come. So this query instance, we can just think of it as a test data. If we have a test data of a patient that we want to predict for, who has reported a symptom of headache, fever, not having fever, and vomiting true. So now when we want to make a prediction, we can plug in each of these instances for accounting for two different levels, possibilities for the target feature, which is having meningitis or not having meningitis, which we'll go over in the next slide, future slides. So the takeaway from here is that we now, since we have data where you can try to get the joint probability distribution of those given some hypothesis, and then compute the posterior probability for each hypothesis for the current query instance, and then compare the posterior of across those hypotheses so that we can choose the highest one with the highest posterior so that we can make a prediction. So from this slide, we can go through one example of, since we know the formula that we are interested in, and we want to compute the posterior for having meningitis, which is the m, which m is the variable, and m is the feature value. Then, starting from the initial belief, or in more straightforward terms, there may be some previous study of probability of having meningitis, which would be an expert opinion. And that is also usually could be derived from the data directly, which is happening in this slide. As we've done in one of the previous slides, we can directly derive the marginal probability of having meningitis, which is 3 out of 10 patients, so 30%, 0.3. And also, when we come to the joint probability of having a headache and not having fever and having vomit, we can similarly compute by checking all the instances where they are matched together, true, false, true. There are 6 of these kind of row, which gives us the joint probability of 0.6. Now the next question is, we have this joint conditional probability. And when without any assumption, we just directly use the chain rule of the probability, which does not make any particular independence assumption, but implicitly assumes that there may be some dependencies between these variables, which the chain rule would be starting from probability of H given M, and then condition that becomes a condition of the next term, and so on. And that can also be derived based on this, derived directly from the table. So now, since we have all of the values for the terms in this Bayes rule, we can compute the probability of the patient having the meningitis given the symptoms of the new patient or the query instance. And then after that, we do something very similar for the other hypothesis, as similarly we can compute this posterior of not having meningitis, which could be compared to this value, which, since it's mutually exclusive, it would be for this query instance, we can make a prediction that this patient with these symptoms does not have meningitis. And this was an example of going through the Bayesian prediction without any type of assumption, which the naive Bayes classifier, which we'll go over, makes an assumption. But in this slide, we just directly utilize the Bayes rule to make this prediction. So before diving into the naive Bayes classifier, we can first go over the independence, conditional independence. So this first set formulas assume the marginal independence. So it's saying that the probability of x given y is equal to just the probability of x. So this is the definition of x and y being independent, because conditioning on y doesn't provide any additional information about the probability of x. And then using this conditional probability definition, we can derive this formula where the joint probability of x and y is just the product of p of x and y. And this can be derived by utilizing the starting from the addition probability. By definition of the conditional probability, we know this is the definition, the standard formula. And since the definition of the independence, the marginal independence, the left term, because p of x, which then we can derive the p of x joint probability of p of x and y. So now this was for the marginal independence. So when it comes to the conditional independence, now we have the another context of the z. So the standard definition of the conditional independence is again this first term, meaning that the probability of x given y and z is just the same as given z. So y doesn't given this context z, y doesn't give any additional independence for x because z was already given as context. So z is serving as a conditioning on z is removing the potentially existing dependence between x and y. So similarly, so this last formula equation is the most important equation for the subsequent slides, which we can derive this formula based on starting from the left term. By the conditional probability definition. And then this joint probability, we can use the chain rule. Which the first term, by definition of the conditional independence, we can substitute and the joint probability of y and z divided by marginal probability is equivalent very sorry about this messy derivation. Where we have could derive this last equation. So what we have done is that we have factorized or broke down this joint conditional probability into a product of smaller conditional probabilities, which was achieved by the conditional independence assumption between x and y given z. And this, without this assumption, the joint probability using the chain rule would have been expanded and so on. So this could the last formula is a more simplified version compared to the term that was derived by the chain rule due to this conditional independence assumption. So, and this this can be pronounced when we so when we have multiple variables. So this slide is basically the extension of this formula, where the joint conditional probability becomes just the product of the individual conditional probabilities because of this assumption, which we can confirm that when there are many independent variables, they are still just the product of the individual conditional probabilities. And if we compare so just using the chain rule without conditional independence assumption, the expansion would be not just the product, but more complex conditionals. Whereas with the conditional independence assumption is simply the product. And so this, with the Bayes theorem, we are going to make an assumption that the descriptive features, which were the headache, fever, and vomit, are conditionally independent given the level of the target feature where this level is corresponding to the target feature is meningitis. And one level of this target feature would be having meningitis. Another level would be not having meningitis. So given that this patient has meningitis, whether they have headache, fever, or vomiting becomes independent with this assumption. In reality, that this assumption is often unrealistic, but we are making this naive assumption, which is surprisingly effective in practice, which we will go over in the next subsequent slides. So now, in the previous example, when we just use the Bayesian prediction without this conditional independence, the joint probability, the likelihood could be expanded using the chain rule, whereas now the likelihood term just became a product of the individual conditional probabilities based on the assumption. So now we can directly compute these compute the posterior based on these factors. But one note is that if we did not make this assumption, then the likelihood term would have been okay, reallocate. Without assumption. And in order to prepare these factors, since we would need to prepare for all of the feature combinations, not HM, and so on. We would need to prepare much more combinations so that we can process a test sample. For example, whereas when we try to compute the second term, P of Fn, which is no longer probability of F given HM, For this, we can just prepare two terms, whereas without the naive assumption, we will need to prepare probabilities, pre-computed probabilities of 4. So this indicates that through this naive assumption, we can save space, because these pre-computed probabilities will need to be prepared before we make a prediction, and also the time complexity of computing all these different additional terms, and um, looking up, because the number of these pre-computed probabilities can be explosive, as we have many more many different features and feature value combinations. So looking up the right term would also add overhead, which, in other words, without the naive assumption, the time complexity and the space complexity would be much more expensive compared to when we have this naive assumption. Okay, so yes, over this slide, we will go over it. So based on the conditional independence assumption, now we are making predictions by using the pre-computed probabilities for the hypothesis of having meningitis, which is 0.948, which was also, because from the Bayes rule, the only change we made from the Bayes rule is that, okay, is that we no longer are applying the chain rule, but applied the conditional independent assumption between the features given the target. But we are still dividing it by the observation, which is the normalization constant. So this means that if we're getting the posterior of having meningitis as approximately 20%, the posterior for getting the mutually exclusive case, which is not having meningitis, is around 80%, which summed to 100%, which was basically the reason why we normalized. But we could further simplify the use. We could further improve for better efficiency in making prediction, because our goal of using this Bayes rule for different hypotheses of having meningitis or not we're just only interested in the classification result. We just want to classify whether this patient has meningitis or not. So does anyone have any uh, thought on how we could further streamline this the computation? Or in other words, is there any computation that's redundant for if you're only interested in getting the classification result? So, in other words, if we are making the prediction by only comparing the relative ranking of these probability, it would be unnecessary to normalize. So even without dividing, even without the denominator, we will get the same order ranking because the denominator is exactly the same. So this would be the additional streamlining of the computation which naive Bayes model improves over the normal Bayes model, which is the Bayesian prediction, which we were went over. So to summarize, two tricks that naive Bayes model does over normal Bayes is that makes a naive assumption of the conditional independence across the features given the target, given some target level. And another trick is ignoring the denominator, which was for normalization. So as we can see in this formally, due to the naive assumption, is just getting the product of the individual joint probabilities of each feature given the target level. So this term corresponds to the numerator of the Bayes rule, and it is comparing against different hypotheses, different levels to make the final prediction. In other words, it's computing the numerator for the Bayes rule for each of the classes having the disease or not, and then comparing their posterior, a normalized posterior, to make the final prediction. So the reason for this conditional independence assumption being naive is because it is unrealistic, and whether it is correct or not, we do not we do not care about whether it's correct or not. So, for example, one known example for this would be if we're doing a text classification task of classifying an email, whether it's a spam email or not. Then, and the features are the words in the email in the message. So if one word is urgent And another feature word is action. Whether an email is labeled or whether an email is spam or not, seeing the word urgent would give some additional information for seeing the word action and vice versa. So they frequently occur together in not only spam emails or non-spam emails, but the naive Bayes classifier with this assumption is assuming that these two words are independent if the email is spam, which is an unrealistic assumption. So that is why this assumption is naive. And also, but even though this assumption is unrealistic, in practice, the naive Bayes approach works very well. And does anyone have any guess or insight why this would be the case? Okay. So, so the reason for the estimated reason for the naive Bayes approach being effective, well, this is not theoretically proven, is that we are just interested in getting the relative order ranking of the unnormalized posterior when the target is having meningitis or not having meningitis. We are only interested in their relative order, whether the posterior for this hypothesis is higher than the other. And we are not, it's our less interest in computing the the accurate posterior probability, which would be obtained through the normal Bayes approach, which when we did not have this conditional independence assumption. So in other words, this implies that even with the conditional independence assumption, the relative order of the outputted posterior probability is preserved, even though we don't get the most accurate posterior probability. So that is one of the explanations why the naive Bayes would work surprisingly accurately, even though it's not the most accurate probability. And also, this conditional independence assumption between the features also has the advantage of the curse of the dimensionality and data fragmentation, which is, in other words, data sparsity issue. So first of all, with the normal Bayes approach, we model the likelihood term as this is feature 1 using the chain rule. And M is for the meningitis. So on. Whereas for the naive Bayes, just product of individual conditional abilities. So with the normal Bayes, these terms, we are basically modeling the feature interactions because we are considering F1 and F2 and F3 all together in each term. But with the naive Bayes, we just simplify that as having the probability of each feature given the target level, so on. So with the naive Bayes, we are simplifying that complex feature interaction where the curse of dimensionality is that for high dimensional data with many features, due to that vast amount of features, there would be naturally complex interaction between those features that most of the machine learning models um, account for. But the naive Bayes classifier ignores such feature interaction, so is robust to the curse of dimensionality coming from very high dimensional data. So in other words, if the naive Bayes classifier is one good option to test against a very high dimensional data. And also for the data sparsity definition is when we say sparsity, it's saying it's not dense, it's many zero terms. So in this case, even though we model considering all of these kinds of feature interactions, such as one example would be our headache, fever, and vomit example. In our pre-computed data, we would need to prepare for all of given M, all combinations. And so on. But as we get more and more features, the likelihood that all of these feature value combinations appear in our training data set would be unlikely. If there's anything unclear about this, please let me know. Meaning that when we are given test data, say having a headache, fever, and not vomit, and many other features, if we are given a test data and we are using the normal Bayes model, we would need to look up for all of each probabilities from a pre-computed table. But the likelihood that these expanded terms exist in our training data is very unlikely, which that compare in a but for the naive Bayes approach, since we are no longer accounting for all this complex feature interactions, we are simply interested in the individual conditional probability, which the combination between H, the headache being 1 or 0, when the meningitis is present. And in the training data, since we're not accounting for multiple feature interactions no more, it's likely that we see these combinations in the training data. So the data sparsity problem is much more mitigated, which that's one other advantage of the naive Bayes model. And the last advantage is that the naive Bayes model is basically preparing for some pre-computed probabilities before testing, where the number of the probabilities to prepare for are much more manageable in size because of the conditional independence assumption. It's relatively easier approach to implement. And when we test, we simply multiply them. So it's basic arithmetic. So it is a model that is easy to implement and train. So so if anyone would have any idea on what a training would correspond to, what would the training process of a naive Bayes model correspond to? Does anyone have any insight on this? Okay. So the training of the naive Bayes could be interpreted as preparing the pre-computed probabilities, since we are not training a specific weight as we did for SVM or other models. The training process is to prepare for the pre-computed probabilities. Okay, so yes, we will take a 10-minute break until first include the probability of the fraud, which is the target, being true, which would be some value. And also we should prepare for the target fraud being false, along with all of the individual conditional probabilities which we would need to compute, which one example would be the accommodation being own, given fraud is true. We would also need the same set given fraud is false. So basically, we're preparing for all of this probabilities. We're pre-computing these, which could appear in the test data, the query instance. We're preparing all of these probabilities so we can make a prediction, which would be any of these combinations. So now we have the test data, the query instance, where the credit history is paid, none, the guarantor co-applicant is none, and the accommodation is rent. So utilizing those pre-computed probabilities, we will make a prediction, which basically here, since we're trying to make a prediction for credit history being paid, the guarantor co-applicant being none, and the accommodation being rent. So if this is our query, which we want to make a prediction for, what we would do is, because the first column is assuming the target is a fraud, and the second column is assuming the target is not a non-fraud. That's not a fraud. So we will plug each of these values in the first column to the naive Bayes classifier the formula, and do the same for the counterpart of not being a fraud, and then compare their posteriors to choose the class that results in a higher posterior that will become the prediction. Which shows in this slide, where now we, for each prediction, this is the unnormalized posterior, where for that this applicant or this customer, that's not a good analogy, that this query instance is a fraud or not, probability for fraud given, and this corresponds to the posterior for not being a fraud. So we see that the posterior for not being a fraud is greater than its counterpart. So for this query instance, the prediction would be that it's not a fraud. Let me know if there's any questions so far. But there's one problem with the naive Bayes, which also relates to the data fragmentation or data sparsity issue that we discussed. It relates to it not directly but indirectly, is that from the prepared pre-computed probabilities, some of the individual conditional probabilities may not appear in our training data set, meaning that our naive Bayes model models the likelihood term as a product of a individual conditional probability for each feature given the target level. But in the training data set, as in this example, there might be zero frequencies, such as for given that the training data instance is a fraud, there's no such case where the accommodation is free. There's no such case, right? So even though our naive Bayes model, in the formula level, it accounts for such case, in the training data, we don't have that. So it's a zero frequency problem where when making prediction, this can be a problem because we are multiplying. This can be part of the multiplication. So if the query instance, the test data, assumes the credit history paid and the GC is guarantor and accommodation is free, there was no such instance in our training data where the accommodation was free. So naturally, the pre-computed probability, the corresponding probability, is 0, which when we try to compute the unnormalized posterior in this case, when we try to compute the unnormalized posterior for the fraud, this 0 probability would make the posterior also 0. And in this example, there's such case for also the non-fraud class hypothesis, which also results into 0, which makes the classification impossible. And this can also be a problem because in this particular example, for both classes, there was a 0 frequency problem. But for other cases, only one class may have this 0 frequency issue. This could be, let's say, it's non-zero, just assuming that zero, some non-zero term. And even if the test sample for other terms might more align with, there could be cases where the test sample's other feature values are more aligned with class, say, A. But because there was this one 0 frequency for some feature, it might result in making a classification for the class B, which, because class A resulted in a 0 posterior, whereas class B resulted in a small but non-zero posterior. So this 0 frequency problem is a main problem of naive Bayes classifier because it relies on the multiplication of all the individual conditional probabilities across the features. Okay, let me know if there's anything unclear about this. Right, so this slide, the takeaway is basically what I've explained in the previous slide. So if there's a 0 frequency problem, then the posterior also becomes 0. So it corrupts the prediction, which needs to be dealt with. So usually when you have this problem related to 0, such as which we saw also in one of the formulas we saw in last class, when we try to avoid the 0 division for, say, the optimizer, the RMS propped, we usually add some small number to artificial number to force the value to be non-zero, which the same idea applies here, where, and we call it smoothing here. And one of the most frequently used smoothing is basically add one smoothing. Where the Laplace smoothing is basically a generalization of the add one smoothing, which adds one. If it's adds one, it's add one smoothing to the count zero count, and could be 2 or 3 and so on. So we're adding an artificial count so that we do not end up with the zero frequency, making the posterior as 0 as well. Okay, so we could try to dissect this formula. So the count of the event, so the original count correspond to this blue section, where a practical example would be that for some feature, let's say, a good example would be that, let's say a feature is named the color. And just assume that the target is, which is unimportant, so just arbitrary label A. And given the target A, the feature of color, which has 3 levels in the feature values, red, blue, and green, has a 0 frequency across 5 instances, has a 0 frequency for red. So, and the frequency for blue is 3 out of 5. And the frequency for green would naturally be 2 out of 5. So from this formula, the numerator, this blue one, corresponds to the original count. And the denominator corresponds to the original total count for that feature. But now, in this example, we see that there's a 0 frequency problem for the feature value of red, which causes the problem we discussed in the previous slide. So we intend to add an artificial value to take care of this 0 frequency value, which we can assume that we go with the add one smoothing strategy. So K is equal to 1. But if we simply add 1 to each, because we cannot just simply add 1 to red, because then no longer the sum will be in terms of proportion. We would need to proportionally add 1 to maintain the balance. We add 1 to each. But if we just add to the numerator of K of 1, then the proportion would no longer sum to 1 in terms of proportion. because after adding 1, there would be 0.2, 0.8, 0.6, which this does not sum to 100% of 1. So for that, we also, to maintain the proportion, this term of we also add to the denominator this term of k times the domain of f, which the domain of f is simply the fact that we have 3 feature levels, and we just set the artificial pseudo count as 1. So for each denominator, to maintain the proportion of addition, we add k times domain of f, which is 3 here. If we do that, then we see that the sum is equal to 1. So the idea is the same for k equals 2 or k equals 3, which by following this formula, you get the sum across a smooth probability. So in other words, this is a smooth probability, whereas this part is the unsmooth probability, pre-smooth probability. You still get 1. And the effect, so now the next question could be, if k is predetermined and could be something as if we have freedom to control it as a hyperparameter, what would be the effect of having a higher k? So the higher you have a k, in short, the effect is that the distribution becomes more closer and closer to a uniform distribution, meaning that you are borrowing more distribution from the non-zero features with non-zero distribution before smoothing to the towards the originally zero distribution feature, which this part I will clarify in the next slide. I don't think I explained it well. So if our raw probability was 0 for the GC being guarantor, causing the zero multiplication problem for naive Bayes, after smoothing, going through using all of these parameters which you saw in the previous slide, and here we see the k is 3, which is different from the previous add 1 example. And after smoothing, we see that the distribution or the guarantor is no longer 0, so it does not cause the zero multiplication problem for naive Bayes. And since it was k was set as 3, we see that the conditional probability of guarantor is lifted to a certain degree from 0 to 0.13. But if we have set k to a smaller number as k1, the degree of the lifting of this probability would have been in a smaller degree. So that would be the effect of having a different value for the k. Any questions? Okay. Okay, so yes, so in the next slides, we will still now we will go to the final part of today's lecture, which is the Gaussian base model. So by its name, we can see that this is going to use a normal distribution, apply normal distribution in some way to the base model, where in the previous examples, we used the naive Bayes for categorical data. The features were all categorical, such as having a headache or not, like binary, mm, or having accommodation or not. But the naive Bayes can also be extended to continuous values, and most commonly we set some probability distribution for a feature that has a continuous values, and one common assumption is doing the normal distribution. But depending on that feature, if we have some knowledge that this feature is, if the data generating process of that feature was a count, then we could use other types of distributions, Bernoulli distribution, or other distributions that make sense with the knowledge of that feature. But typically we use the normal distribution. So the only difference with the naive Bayes we saw from before is that the feature can be continuous, and all of the other assumptions of naive Bayes, the naive assumption of conditional independence between the features is still preserved. So one visual example to demonstrate the difference in the feature would be the categorical data set we saw look like true and false, so on. Now our current data set could be modeled as height, which could be real values, or other types of numerical features. And one caveat is that it is possible to apply the naive Bayes to data sets that are have both categorical features and numerical features. So that is also a use case, an approach that people use. But for this Gaussian based model, we will first focus on this type of data set where the features are continuous. And the target here, we still assume as discrete. But the Bayesian model itself can be applied with continuous target. For one example, which we will not go over, so the point I'm making here is that Bayesian model is not confined to the target being a categorical feature, but also could be extended to continuous setting where the target is continuous, which one example for that would be we would want to estimate the average effect of a drug, which that average effect could be some percentage as 2.1 percentage given our experimental features. We want to we want to compute some posterior for the average effect for some target variable, which is the drug's true effect. Then that would be a scalar. The target numerical feature would be a number. Or other use case would be that the target could also be a vector such as a model parameter, such as in Bayesian neural network. The target is a set of continuous values where we start with some prior of our belief that some vector captures the true is the ideal or so starting from some belief on the weight vector, we try to approximate some probability distribution for the target. But this part, I don't think I may explained it very clearly, but so if you are interested, you can look into the Bayesian neural network, which is, I diverged a little bit. So coming back to the case where our features are continuous and the target is still categorical, we can see how this applies. So for each feature, let's say we have one feature which with continuous values. Then for this feature, we will be able to get its mean and also its standard deviation, which so for this particular feature, we have get two parameters which summarizes these features. And we can have for each other continuous numerical feature, we can have their respective mean and standard deviation. So in the next slide, if we see, this is just making point that we have how to compute mean and standard deviation. Yes, so given that from our training data set, feature 1, feature 2 with two features, with the target, now we know that we can prepare for the first feature's mean and the standard deviation. And also we can prepare for the second feature's mean and standard deviation of the second feature. So now, but the reason for computing these, so these correspond to the pre-computed probabilities in the categorical setting, which we went over before. So these feature-specific normal distribution parameters correspond to these pre-computed probabilities in the categorical setting. There's a correspondence between these. One feature is a categorical, one feature is numerical. So since we now are prepared, we have the pre-computed some equivalent to the pre-computed probabilities in the continuous feature setting. Now we can plug in new data, such as for the new data X, which is basically the query instance equivalent, could be for the first feature, it could have the value of 7 at 2 of some other numerical value, which for each feature we know that we have its corresponding mean and corresponding standard deviation. So we can plug in for the first dimension f1, x is f1 to this value, and the corresponding mean here. So we're plugging in x into the probability density function to get the probability density of x from the normal distribution that was generated based on the feature values here for this specific f1 feature. So the output can be interpreted as the probability density of the new samples corresponding feature value, f1's feature value. How likely, or if the higher the density is can be interpreted as this new data's f1 feature value aligns more with that of the training data's across the training data's f1 feature values. So it more resembles it. And same for the f2. We get the same probability density for f1 and f2 separately. So this is equivalent. It corresponds to the posterior in the categorical setting. More specifically, this corresponds to one of the terms that we multiply within the likelihood setting in the given. So for each feature, we get its probability density, which will be multiplied within the likelihood term as we multiplied for the conditional probabilities in the categorical setting. So one working example is this as same as in the previous example. Now the features are continuous, x1 and x2, and the target is discrete. So as we discussed in the previous slide, we will compute target specific mean and standard deviation, which I forgot to mention in my example. So this is exactly same as we have seen these terms. Individual conditional probabilities are exactly what we saw in our categorical dataset setting. So we are doing the same idea, just using continuous valued features, but summarizing them based on some probability distribution parameters, mean and standard deviation for the normal distribution. Let me know if this part is unclear. Anything unclear? So now so given the new test data, this is the new test data. X1 is this value, X2 this value, and its ground truth label is y equals 0, which is the true label. For prediction, as because we have already we are prepared with the X1 features, mean and standard deviation, we already computed, and we have the same for X2. We can now plug in for each dimension, each feature, given a specific class. So more specifically, we have class specific feature, standard deviation, and mean. And so on. So by plugging this in, since the naive assumption still holds, we do not assume any dependency between the numerical features x1 and x2. That assumption still holds. So we still simply multiply them also with the prior. And the other parts are exactly the same, where we get the PDF and then probability and multiply them as we did in the categorical setting and compare their final posterior, normalized posterior, to determine which class this new sample should be predicted as. And in this case, the class zeros on normalized posterior is higher than class ones, meaning that the Gaussian naive Bayes correctly predicted the sample as having its true label of 0. which is basically this slide is showing. Okay, so the lecture is over, and in next Monday, next week Monday, for the first half, we'll have quiz 3, which the quiz 3 will be in a different format as with Jacqueline, and will be quizzes and assignments will be generated by the Blossom AI. So now I am in discussion with the Blossom AI people. So the details on the quiz will be shared later this week. Yes, so that's about it. You think someone wrote the chat? Yes. Yes, you should send an email for the attendance. Were you not here at that time? Yeah, you could send to this.